Okay, today we're going to talk about our different conic sections and the different equations for them and how to graph them given the equation or come up with the equation for them. So we'll start with our essential, actually this is assignment 17, so let's write that first. And then our essential question, given an equation for a conic section, how do you plot the graph? And given the graph of a conic section, how do you write the equation? So given an equation for a conic section, how do you plot the graph? And the converse of that, so given the graph of a conic section, how do you write the equation? And I'm going to do this lesson over 3 separate videos. So today will be the first video for day 1, the next one will be day 2, and the next one will be day 3. Okay, so we're going to start by reading page 496 in your textbook. Just a little review, kind of some stuff that I went over yesterday as well. Let's see where that is. All right, so this is page 496. The paths of satellites or comets traveling in space under the action of gravity are called circles, ellipses, parabolas, and hyperbolas. And as many of you know, we use a lot of internet, cell phones, technology, and all of that stuff is based on or works from satellites. So the people that are creating those satellites and putting those satellites into orbits are using these equations on a daily basis to make sure that they are following the trajectory that they need to. Without this, we would not be able to use our cell phones. Okay, so figure 10-2a shows how these conic sections are formed by a plane sectioning one or both naps of a cone at various angles. So you can see that there are 2 parts to a cone, like this top cone and the bottom cone. Those are called naps. And the plane, like I showed you in your last video, is basically intersecting this cone at different angles. And then the graphs of these quadratic equations in 2 variables are conic sections, as you saw in 10-1. So what you can see here is if the plane enters it perpendicularly, you get a circle. And then as we get these tilts or these angles from the perpendicular, we get different conic sections. So an ellipse is basically a circle that's been dilated. A parabola, you can see this tilt here is creating just part of that ellipse. And then once you get a pretty extreme tilt, the plane ends up intersecting both naps, and you end up with a hyperbola that basically has 2 branches. Down below, it says, you may have seen shadows cast by a cone of light from a floor lamp that is cut by the planes of walls and ceilings, as seen in figure 2-b. Let me scroll down a little here. The wall cuts both naps of the cone, forming a hyperbola. The horizontal ceiling cuts the cone at right angles to its axis, forming a circle. So you can see we've got this one over here, forming that hyperbola. This one over here, horizontal ceiling, we get a circle. This one over here, a slanted ceiling, we're going to end up with an ellipse. The sloped ceiling can form an ellipse, a parabola, or a hyperbola, depending on the slope. So just a couple of examples of where we're getting these conic sections from. But basically, by the time we're done, you should be very familiar with the equations of circles, equations of ellipses, equations of hyperbolas, and equations of parabolas. Okay, so moving on from there, we are going to look at our handout here. All right, so and we've talked about this with our parent graphs, but basically the equation of the unit circle is x squared plus y squared equals 1. Now again, if you're going to have any dilations happening or if you're going to have any transformations happening, you're going to have some h's and k's and some other coefficients. Okay, what's important to remember though is that in a unit circle, the coefficient of these two are always going to be the same. You then have a unit hyperbola opening in the x direction. We know it's opening in the x direction because you can see that this is actually facing, right? This opening here is towards the x. It would be a y opening, right? If you're opening along that y-axis, okay? So when it's opening in the x direction, you're going to have a positive x. So this part right here is positive. And when it's opening in the y direction, what's positive? The y term, right? The y coefficient. So this one is going to be positive. So that's how you know which direction your hyperbola is opening. Okay, the next thing we have is the unit parabola. So all this saying that it's a unit means it hasn't been dilated at all. Unit parabola opening in the y direction. Now you're very used to seeing this, right? The y equals x squared. So this is when it opens up or down, and this is when it's solved for y. The unit parabola opening in the x direction, or basically that parabola on its side, is when it's solved for x. And as we continue in math, we begin to see many, many, many of these. Okay, this is basically what I wrote down in your notes yesterday, right? So this, or in your assignment, I should say, this stuff right here on number 8 is basically what was leading up to this. So quadratic equation in 2 variables has no xy term when the graph is, well, no xy term means it doesn't have like 3xy, right? It's got an x squared term and a y squared term, or an x term and a y term. So a circle, if the x squared and the y squared have equal non-zero coefficients. You don't want 0 because then you don't have an x or a y. An ellipse, if basically they have unequal coefficients, but the same sign. A hyperbola now, if they have opposite signs. And a parabola, if only one of the variables is squared. That's exactly what we went over in our last video. Moving on. Now we're going to see some transformed conic sections. So if you start with, for example, this dotted circle, this is the unit circle. It's got a radius of 1. Okay, but now look what's happened. We've got this shape where along the y-axis it's stretched from +3 to -3. And along the x-axis, well, if this was 1, this is probably going to be 2. I know it doesn't show that, but it's going to be 2. So here we have a y dilation that equals 3. We have an x dilation that equals 2. Okay, this is an ellipse. Okay, this is basically we've taken that unit circle and we've dilated it, and we haven't dilated it the same amount. So the radius is not the same all around. Okay, instead what we end up having is a major axis, which is going to be the y-axis because that's the longer one, and then a minor axis, which is going to be your x-axis. So this is what we call a dilated unit circle which we would then call an ellipse because the dilation was not consistent all around. Now the general equation for an ellipse is right down here, and you can see that basically you're going to take x minus h, so if you have any transformations, if it's not centered at the origin, then hk will be your center, okay, and then these dilations, so this is like your dilation of the x-axis, your dilation of the y-axis. So we're going to use this right now to help us come up with an equation for this ellipse right here. Okay, so first of all, this thing is still centered at the origin. So then that tells me that my hk is 0, 0. So I don't need to worry in this equation about having an h or a k. It's basically just going to have an x on top and a y on top. And then I'm going to put my dilation factors down below. Now again, it was a y dilation of 3, so that's going to go below my y, and an x dilation of 2, so that's going to go below my x. So I'm just going to, my equation will look like this: x over 2 squared plus y over 3 squared equals 1. Because an ellipse always is set equal to 1. Now this one to the right here, not only do we still have those same dilations, right? We got a y dilation by 3, an x dilation of 2, but my center has been translated. Okay, so my center is no longer at 0, 0. It's been translated to the left 4 and up 1, making my h negative 4 and my k positive 1. So now when I use this equation down below, I do have an h and I do have a k. My dilation factors stay the same. Okay, so this equation here then is going to have the exact same dilation factors. The only difference is that I now have an h and a k. So it's x minus h. Well, x minus negative 4 is going to be x plus 4 over my dilation factor of 2. And then y minus k, well, y minus 1 over my dilation of 3 equals 1. So those are how you take the graphs of these ellipses and you come up with actual equations of them. All right, so we've got a whole bunch more here. So the circle, again, we did the circle in geometry. Okay, so you can either write it where you have your transformations and you set it equal to your radius squared. You can set it equal to 1, but in order to do that, you're going to basically have to divide both sides by your radius squared. Okay, so that's where these r's are coming in here, giving your x and your y still the same coefficient. So like if the radius was 5, let's say, then this would have a coefficient of 1 over 5 squared, or 1 over 25 if I moved it outside of the square. All right, you also have your hyperbola, and we talked about the hyperbola will open in the x direction if the x squared coefficient is positive, like this one, or in the y direction if the y squared coefficient is positive. The dilation factors help you figure out your asymptotes. So your asymptote, and it says it down here, the asymptotes are always going to be the y dilation over the x dilation, and you're going to have the positive and negative. And that's for both of these here. And your center will always be at hk. So if the center is still at the origin, then there is no h or k. And then lastly, parabolas, which we've done a whole bunch of work with. This one should be pretty similar or pretty obvious to you. I've always put the plus k at the end. Notice they've got a positive k in the front. Okay, if this was shifted down, it would be a negative k. This would still be a plus. Okay, the k itself, if it's shifted down, it's negative. If it's shifted up, it's positive. Okay, and then if you open it in the x direction, it's solved for x, your y is squared, and therefore the x and the y have been interchanged, and so now it would be y minus k squared. Again, notice that your horizontal, or your h, now is out here, okay, and your k is inside. Your vertex still at hk. All right, we're going to do a couple of examples together. Let's see, I think I have 2 examples on this video. Yep, so we'll do 2 examples. I'm going to use graph paper because we're going to be graphing. So this will be day 1. We're going to do example 1 and example 2. All right, so example 1 is to sketch. And here it is. You're going to have x minus 2 over 5 squared plus y minus 4 over 3 squared equal to 1. So before you can even figure out how this is going to look, and I wouldn't just jump into Desmos, you need to make sure that you can actually use your brain on this. You're going to want to go over the rules that we originally had talked about. So I'm looking at my coefficients of the x squared and the y squared. So the coefficient here, if I pulled this 5 out, this is 5 squared, would be 1 over 25 for the x squared. And if I pulled this 3 out, well, that's 9, right? So it'd be 1 over 9. So the coefficients of x squared and y squared are different. They're both positive. They're both squared. So let's go through this. Well, it's not a circle because they don't have the same coefficients. They do have unequal coefficients, but they do have the same sign too, right? Not opposite signs, and not just one of the variables being squared. So it's definitely an ellipse. I'm going to go ahead and just jot that down so that you have it in your notes. We know it's an ellipse because the coefficients are different. But they have the same sign. So that's kind of the process that you want to go through and thinking about, hey, which conic section is this? Now I'm going to look for my h and my k to figure out where my center is. And I can see that my h is a 2, my k is a 4, so my center will be at 2, 4. And then the last thing I'm going to do is I'm going to figure out my dilations. So it looks to me like I have a horizontal dilation of 5 because that goes with the x term. I can't think of the word. And then I'm going to also have a vertical dilation of 3 because that goes with the y term. Okay, so we've got horizontal dilation, which is going to be 5. Vertical dilation, which is going to be 3. So that tells me that my x-axis is going to be my major axis because it's longer. And then my vertical axis will be my minor axis. And then I'm just going to go ahead and graph this thing. So let's see, where did I put my ruler? All right, so this thing, oops, this is going to have to go up because it's been moved. So let's see. 2, and then 1, 2, 3, 4. Oh, and from there, I'm going to have to do a vertical dilation of 3. That's okay. I think I can make this fit. It's just not going to be the prettiest thing ever, but that's okay. All right, so here's my center. And then I'm going to have a vertical dilation of 3. So I'm going to go up 1, 2, 3. And down 1, 2, 3. Putting my lowest point at 1 and my highest point I think this is 4, 5, 6, 7. Okay, and then from there I'm going to now do my horizontal dilation. So from the center I'm going to go to the right 1, 2, 3, 4, 5. And I'm going to go to the left 5 as well. 1, 2, 3, 4, 5. So if this is 1, this should be, or sorry, this is 2. Let's label these so I know what I'm doing. And I've gone 5, so I should be at positive 7. And then I've gone 5 to the left, so I should be at negative 3. Okay, so my ellipse will look something like try not to make it like too pointed. Should be curved. Do the best that you can. So I have my minor axis here. Let's see, I'll label it like this, minor axis. And then my major axis is my horizontal axis. Okay, so the minor axis is always the smaller axis. The major axis is always the longer axis. We call the ends of these axes the vertices. So let's see, 7, 4 is going to be so on the major axis, the vertices, which are really the ends, are going to be at 7, 4, which is this one right here. And then the other end is going to be negative 3, 4. Okay, so on your major axis, you'll have your vertices. Again, those are the ends, and those are the two vertices that we have. All right, moving on to example 2. Let's do one more of these. Now we're going to sketch. This is going to be a negative x plus 5 over 2 squared plus a y minus 4 over 3 squared equals 1. So the first thing you want to do is you want to identify what type of conic section this is. Now I see that both my x and my y terms are squared, so I know it's not a parabola. I see that the coefficients, right, so the coefficient of this one would be like negative 1/4. The coefficient of this one would be positive 1/9. So I see that they're, first of all, they're not the same, so it's not a circle. And then I see that they're not the same sign, so it's not an ellipse. So they have opposite signs, and the coefficients are not equal. Therefore, they have opposite signs. We know that it's a hyperbola. Okay? So let's go ahead and write that down. Just thinking of our Okay, I'm doing great. Hyperbola. Okay, now why is it a hyperbola? Basically, coefficients are not equal. And we have opposite signs. That's the key right there, the fact that we have opposite signs. Okay, so we know that it's a hyperbola. Let's see, we also know its center. So if you look at your h and k, the center is going to be at negative 5, because this is a plus 5, right? So negative 5, 4. We know that it opens in the y direction because the y is the positive term. So just to remind you here, when we look at hyperbolas, right, it's either going to open in the x direction if the x squared coefficient is positive, or it's going to open in the y direction if the y squared coefficient is positive. This is what we have happening. So it opens in the y direction, like up and down. Okay, I think we've got all of our notes there. Oh, we need one more thing. Slopes. So what are our slopes going to be? Well, you get your slopes by basically taking the y dilation factor and putting it over the x dilation factor. So our slopes are going to be positive and negative 3/2. Slopes of the asymptotes, positive and negative 3/2. Okay, and that again was right here. We circled that on our notes. Both of them, they're the same. All right, so when you graph these, it's a little bit more tricky then graphing some of the other conic sections, I'm going to think to myself where my center is first. So -5, 4, that's what I care about. So let me go there. So I don't need too much negative space here. Okay, now we use our dilation factors to draw kind of a box. It's going to usually look like a rectangle. So in the y direction, I'm going to go from my center, I'm going to go up 3, which should put me at 7. And I'm going to go down 3. Which should put me at 1. And then I'm going to use my horizontal dilation factor. So from my center, I'm going to go over 2. Put me at -3. And then the other direction 2, which will put me at -7. And then I just draw this box here. Now my asymptotes actually go through the corners of the box, which would make sense, right? Look, the slope from the center is going to go up 3 over 2. Okay, so this is my asymptote with the positive slope. It's going to go through these 2 points. And then with the negative slope is going to go through the other 2 opposite vertices of this box. So you can always double check that you have the right box made by double checking your slopes. So again, it was supposed to be positive and -3/2. This one we already checked was positive 3/2. This one is going to be -3 over 2. Okay, and then we now have these 2 parts of our branches that are the vertex. So the box shows you exactly where the vertices are going to be. You're going to have a vertex because it's opening in the y direction. You're going to have a vertex at the top part of this box, just above the center, and at the bottom part of this box, just below the center. Okay, so these are your 2 vertices. And then from there, you just basically draw parabolas, right? The 2 branches opening towards the asymptotes. And if you wanted to plug in actual points and get inputs and outputs, you could totally do that too. I'm just going to go ahead and draw. We're getting a basic understanding of how to draw these things. I think we're pretty good. Okay, so we're going to call these 2 points right here, because it's opening in the y direction, these are our vertices. If it was opening in the x direction, then these guys would be our vertices, but it's not. It's opening in the y direction, and the reason we know that is because the 3 here is bigger than, or sorry, wrong one. Because the y is the positive, right? So the y squared is your positive term, and that's why it's opening in the y direction. Okay, that's the end of our lesson today.